Hello everyone, I hope you are doing well. In this video, we are going to solve problem 10 from chapter 7 of Introduction to Statistical Mechanics by Roger Bowley. The chapter name is Maxwell Distribution of Molecular Speeds. Okay, and we have uploaded many other problems, the solutions to many other problems from the same chapter. Practicing those problems will help you to prepare for exams very well. And before practicing problems, I advise you all to go through the topics first, because it makes your mind clear about the terms being used and the formulas being used. So yes, some of the key concepts from this chapter were density of states and their expression in terms of k space, e space, how to convert them into each other. Then after that we saw the molecular distribution of speeds formula by Maxwell, and some other stuff related to that. This problem specifically is also related to Maxwell distribution of molecular speeds, the actual formula. Okay, so let's see the problem statement and then we'll dive into the solution. Here we can see the problem 10 right here. What fraction of hydrogen gas molecules at sea level, okay, we are considering this case at sea level. We'll see what that mean and what effect it has on the things that we take. So yeah, we have to find out the fraction of hydrogen gas molecules at sea level and at this temperature, which is 300 Kelvin, that has sufficient speed to escape the Earth's gravitational field. Leave your answer in integral form. That's the best thing they have done for us. we don't have to solve that integral. We'll just need to write the integral, and that's it. And what we have to do is to write an expression for the fraction of gas molecules of hydrogen molecules which have sufficient speed to escape the Earth's gravitational field. And there is a concept, there is a specific speed that we call as escape velocity. This escape velocity is the minimum speed required by a particle or an object to leave the Earth's surface. That is the minimum sufficient speed. If the object has that speed, then it can escape the Earth's gravitational field. Okay, all of the gas molecules of hydrogen which have speeds equal to or greater than escape velocity would or can escape the Earth's gravitational field. Okay, that is the basic thing that we'll keep in our mind while solving the problem. All of the gas molecules that have speeds lesser than the escape velocity couldn't escape the Earth's gravitational field. So what we have to do is to find out the fraction. That fraction means okay, let's proceed with it step by step. Okay, so solution. We know that the Maxwell distribution of molecular speeds have following formula. Which shows the number density of gas molecules in the speed interval du. Okay, and the formula is, let me see, I have write it here because it's a lengthy one, and it's for a free particle u square e to the power minus mu square by 2 kb t and du. Okay, this is a whole constant quantity. Lambda d is the thermal de Broglie wavelength, and all of these quantities are constant. Here u, which is a variable, Here is the U, which is variable. M is the mass of the gas that we are considering. Okay, Kb is Boltzmann constant. T is the temperature that we are considering, which is given to us, and that temperature is 300 Kelvin. And besides that, we also know the mass. The mass is for hydrogen gas molecules, we can easily calculate it. But since they have told us to leave the answer in integral form, then it's not necessary to insert these values, but it's an additional thing that you can do. Okay, this is the general formula for the number density, and that shows the distribution of molecular speeds, that how much of the gas molecules are available in du interval, which means that, for example, if we are considering that how many gas molecules, the number density of gas molecules that have speeds between 30 and 32 meter per second, for example, in that interval, this formula will give you the number of gas molecules per unit volume that have these that have speeds in between these, okay, in that interval. So we are considering uh, we are representing the interval by du sign, which shows the interval under study. So we want to find out the fraction. If we integrate it, okay, we'll not integrate it right now, I'll do that thing later. uh, let us call this thing without that integral sign as equation number 1. Now I took this formula. This is the formula for a free particle, and since we are considering the hydrogen gas molecules at sea level, the gravitational potential energy, or this is a reference level in which we consider that the only energy that gas molecules have is the thermal energy due to temperature, that is 300 Kelvin, and it doesn't have any gravitational potential energy. So it can leave the Earth's gravitational field if just uh, with the aid of the thermal energy that it has. Otherwise, it doesn't have any other energy. So there is no potential energy that the gas molecules have at sea level, and that's how it affects. And now we number density of hydrogen gas molecules that have speeds equal or greater than equal to or greater than escape velocity. Let's say escape velocity, yes, spellings, let us denote it with small v with e in subscript. Okay, that shows escape velocity. All of the number density, we want to write the formula for the number density of gas molecules that have speeds equal or greater than the escape velocity. So it is given by, let us call it as capital N E, okay, that can escape. So it will be given by this integral, n of u du. Will integrate it because we want it, the speeds varies from ve, from escape velocity, to infinity. Okay, all of the gas molecules that have speeds from ve to infinity, if we integrate this thing between these two limits, it will give us the total number of molecules, the number density of gas molecules that have speeds in this interval. Okay, so we'll integrate it. We'll write all these things. These are constant, so they will come out of the integral. Simply we write it like that with limits of integration. Let us call it as equation number 2. Okay, and the total number density of hydrogen gas molecules that have speeds from 0 to infinity. So it covers all the gas molecules. For example, we had 50 gas molecules, the total number of gas molecules and their speeds could be 0 to infinity, and out of which maybe 5 are the ones that have speeds equal or greater than escape velocity. So what we are doing is we want to find out the ratio, the fraction. So 5 is the number density, for example, of molecules that have speeds greater or equal to escape velocity divided by the total number of molecules, all of the molecules with all the speeds that all possible number of molecules. So this is what I'm writing here. So let us call it as n naught, which shows the total number of molecules or number density. So the limit of integration will run from 0 to infinity because it includes all of the gas molecules, and we'll simply write it as rest of all the things remains the same because we are considering the same molecule or the same gas. Okay, since we want to find out the fraction, we'll divide both of these expressions, dividing 2 by 3. So this one will come in numerator and it will come in denominator. Okay, this is the total. Fraction means given value divided by the total value. So this is the given value and this is the total value, and ne by n naught, that gives fraction. Let us call it as f. That would be equals to ve small e to infinity n lambda d cube m cube 2 pi square h cut cube u square e to the power minus mu square by 2 kbt du 0 to infinity. And this one formula here, u square e to the power minus mu square 2 kbt du, and since these are constant, they will cancel out. These things couldn't be cancelled out because they are variables and the integration has to be performed first, and since we were told to not do the integration, such a lovely thing that they have told us to do to not do this. And yes, this is the final integral form, and this gives us the fraction of molecules that could escape the Earth's gravitational field, and this is the final answer. Okay, this is escape velocity. Okay, this is the final answer, and you can also put the value of temperature kb multiply by 2. Okay, you can solve it. You can also find out the mass value, the mass of hydrogen molecule. We know that the mass of one atom is given by number of moles multiply Avogadro's number gives you the number of molecules, and if you want it to be equal to one atom, then the mass, our molar mass Na equals one atom, m equals molar mass divided by Na. That will give you the mass of one hydrogen atom. Okay, molar mass of hydrogen atom is 1, and to be specific, you can see on internet whether it is 1.0073 or something like that. You can even put that one thing, put the value of Avogadro's number. Okay, and since they are in grams, you have to convert it in mole per grams. Okay, you have to convert it into kg, and you will insert it. You will get the mass of one hydrogen atom. You will multiply it with 2 to get the mass of hydrogen molecule, and then you will divide it with 2 kbt to insert the value right here. That's optional, you can do that. And yeah, that is how the problem 10 is solved. And we'll see you in next problems. Take care and good luck. I'm making this video at 2 a.m. Just because some of you have told me that it's your exam on 10 January. Oh, sorry, 10 June. My mind is not working. So I'm trying my best to upload as much as problems and lectures as possible.